Hello everyone, I hope that you are fine. So today's lecture is about mobile robots. In the previous lecture, we talked about types of mobile robots. And there was also a book, the second book, about mobile robots. We changed this book and the alternative book is Elements of Robotics. So let's start the lecture. In today's lecture, we shall first define navigation. After that, we shall talk about autonomous navigation of mobile robots. Then we shall discuss about navigation by odometry. We shall see that what is odometry, how can we calculate the distance traveled by the robot. Then we shall learn about localization and how the robot can localize itself in the environment. After that, there is a explanation for robot's pose. What is a pose of the mobile robot? Next comes mapping. We shall define what is mapping. How can we do discrete mapping of the environment? Then we shall have a brief introduction about robots architecture. We shall discuss 3 different paradigms of robot control. Then we shall talk about what are the algorithms. What are the different types of algorithms? And we shall also talk about the performance parameters of algorithms. Finally, we shall learn about bug algorithm. We shall see how they work for autonomous navigation of mobile robots. Navigation. What is navigation? Navigation means determining self-location in environment, finding the path toward the destination while moving on the path and avoiding obstacles. Let's see the example of how humans used to navigate in the history. So they needed a map of the environment, and then they needed some kind of direction finding equipment such as compass. So they see this on this map, they see okay where they are now, where they are located now. They can do it using some kind of the signs of the cities, the name of the cities, the name of the villages, or using some famous places and then matching them on the map. And then they use this compass to find the direction of their motion, direction of their travel, you can say. So this is navigation, to the ability to locate oneself in the environment or in the map, and then finding a path or direction toward your goal or your destination where you want to go. Same thing we do nowadays with our smartphones and using Google Maps and GPS. So the Google Maps provide us the map of the environment, and then we use GPS to locate ourselves on the map. Okay, and then there is also a compass that tells us the direction where we want to go, where is our destination located. So navigation can be in different types of environments. It's not always outside with GPS, but sometimes it's the indoor environment. Indoor environments are, for example, navigation inside the room. In the first lecture, we discussed about the mobile robot that cleans the room. Okay, this is the indoor environment where the mobile has to localize itself, where the robot has to navigate, avoiding the obstacles. So this is the example of indoor environment. And then we have navigation in the outdoor environment. The outdoor environment navigation is, as we already seen this example, we can use GPS there, and it's relatively easier as compared to indoor environments. Then we have static environment. Static environment means the obstacles in this environment are fixed, they are not moving. So the objects in the environment, they are fixed. One of the examples of static environment is the industrial environment, where the robot arm has to pick and place. So because it's not that only the robot arm has to move, but other objects in the environment, they remain fixed at their original location. So this is an example of static environment. Then we have dynamic environment. Dynamic environment is more closely related to the real world scenario. In dynamic environment, the objects or the obstacles, they are moving. So the navigation becomes more challenging task, because there are unexpected obstacles on the path of the robot, which was not there before. Okay, so now we shall discuss about the autonomous mobile robot navigation. So how robots can autonomously navigate. Autonomous means they have the ability to navigate in the environment without human intervention. So they can make their own decisions without the help of human beings. So typically the robots that has to autonomously navigate, they should have a very powerful perception. They should have very good cameras and other sensors, and then a powerful computer, embedded system. So typically what they do, what they're doing here, so they get information from the environment using sensors, and then this thing is called perception. Perception means to extract useful information from the data, from the sensors. And after that, the robot performs localization and mapping. The robot knows that where it is located. Okay, and then it also knows that where the obstacles are located, which is a mapping procedure. Okay, once it has this, the robot knows where it is in the environment and what our environment looks like. Okay, then it can do path planning. Path planning is a process of making paths to the destination from start position, avoiding obstacles, or meeting some kind of other criteria to minimize energy or time. Then comes motion control. Motion controls means the robot has to follow the path. It also has to control the position and orientation of the robot, so it can stay on the waypoints and reach the destination. So this is a typical steps going on in the autonomous navigation of a mobile robot. Navigation by odometry. Odometry means that, okay, let's see, the odometry is the measurement of distance traveled by the robot with respect to initial position. So odometry is, you can compare the odometry like a human walking with closed eyes, okay, just by counting the number of steps, and then after counting certain number of steps, the human can tell, okay, how much distance I have traveled. So same thing is for robots. Robots can also tell, just counting the number of steps they have taken, and then they can tell roughly or inaccurately that how much distance they have traveled. So this process is called odometry. Mapping motor power into velocity and then using this equation, okay. So one of the simplest way to calculate the distance traveled by a robot is using the equation of motion. So how we do that? We calculate the power consumption of the motor, and then we try to relate that how much velocity is there for this specific power. Okay, we find the velocity for a given power, for the fixed constant power, and then we also calculate the time taken to reach the next position, and from there we can calculate the distance traveled. So let's see this example. Let's say this is the initial position of the robot, position number 1, and robot has moved from this position to position number 2, and it has a velocity v, and time taken is t to reach this position. So the distance traveled s can be calculated using this equation of motion here. So this is the simplest example of odometry. Of course, this is I have taken the linear model of the odometry. It's only the linear motion for simplification. But if you take some turns, then it will become more and more complex. Okay, but the problem is there is this kind of odometry. It's very inaccurate. It's very because sometimes there is not accurate mapping from power to velocity. This is not always true because there are many factors that affect this kind of relationship. So sometimes the relationship is not linear, it is non-linear. Sometimes there are other environmental factors that affect this. So this type of odometry is not accurate. So let's see what other types we have available, how we can do odometry using other methods. So there is a very famous one. It's using wheel encoders or wheel encoders based odometry. So what we have here in this type, we have a robot with 2 wheels, and in these 2 wheels there are optical encoders are attached, which can count the number of rotations of the wheels. What we need to do is we need to know the diameter of the wheel and rotations, number of rotation of the wheels. So if we have these 2 things, then we can calculate the distance using this equation. Okay, so this was the position 1, this was the final position 2 of the robot, and the robot moved, let's say, in a linear way. So there was no turning, just a linear motion. So just using just counting the number of rotations, okay, and using the radius or diameter of the wheel, we can calculate the distance traveled s. Again, there are problems with this kind of odometry also, and the problems are that it may be unreliable, the measurement is unreliable, it can be nonlinear, time varying. So, and what causes these all errors in the odometry is the slip of the wheel, because the surface is not always perfect, okay, and sometimes the wheels slip on the surface, so they miss this kind of measurement. And then we have unequal size of wheels. Sometimes the wheels are not perfectly equal, so the left wheel is a little bit larger than the right wheel, and then this also creates problems. Also, the misalignment of the wheels. So sometimes the axle is not perfectly aligned, and this makes the wheels not equally aligned with each other, which again causes problems and errors in the odometry. Finally, we have an issue with the road, which is realistic. The roads are not perfect. There are also some ups and downs where the wheels can they can slip or they can get stuck. So all these factors, they causes errors in the odometry and make the measurement unreliable. So there is also another method for odometry, and this is using inertial measurement unit or IMU sensor. So in the first lecture, in the previous lecture, we discussed about what is IMU sensor, and now we see that how we use it for odometry. So we know that from the previous lecture, we know that in the IMU sensor there is an accelerometer that can measure the acceleration, and then there is a gyroscope that can measure the velocity, angular velocity. So using these two sensors, we can calculate the linear acceleration and angular velocity of the robot. Okay, so once we have acceleration, we can calculate the distance traveled in the linear direction. And by integrating the acceleration, we can calculate the distance traveled, because the derivative of distance is the double derivative is the acceleration. So using the double integral of the acceleration, we can calculate the distance traveled in a single axis or in a single direction. And then we have angular velocity. So from angular velocity, we can integrate this velocity and then get the angular position theta. So using this IMU sensor, we can calculate the position and orientation of the robot. But again, this kind of odometry or this kind of sensor, this is also there are also uncertainties and errors in this kind of measurement, because IMU sensor is highly sensitive to temperature and also the jerky motions. So it can also give false measurements. So these kind of sensors, they are commonly used in combination with GPS for better results, and sometimes they also have integrated compass, electronic compass, to also improve the results. Now we shall see what is localization. In the previous slide, we have learned that the odometry is not the best solution to calculate the position of the robot. We have seen that odometry is like walking, counting your steps and closing your eyes, and then walking, and then try to estimate how much distance you have traveled. So this measurement is unreliable. So we cannot totally rely on odometry from encoders or power to velocity mapping or IMU. We need some other external methods to calculate the position of the robot in the environment. So let's first see what is localization. Robot localization is a process of determining the location of a mobile robot with respect to external reference whose location is already known. So in the localization, what we do is we try to find the location of the robot using an object in the environment whose position is already accurately known. So this is how we do localization. Lines on the road, windows, doors of buildings are examples of landmarks that can be used for localization. So in the environment or in the map, there are always landmarks. Landmarks are some distinct objects that can be recognizable, and they can be used to find the location of the robot, because their own location is accurately known. So during localization, we assume that the map of the environment is already known, and the robot is equipped with sensors to observe the environment and also to monitor the motion of the robot. So this is required for localization. So localization can be used to further reduce the errors in the odometry and improve the measurement of the position of the robot. So this is an advantage of localization. So now how can we calculate the position in actual? Now we shall learn about it. Determining location from objects whose position is already known. So we have one object, this one here. This is an object we have, and this is our robot. So this is a special method of calculating the position of the robot, and in this case what we have a angle and a distance from this point is already known. For example, this distance S, let's say this is S, and the angle, this angle, let's call it phi. So these two measurements are available. And how they are available? So the robot has some kind of sensor that, let's say, a laser scanner. A laser scanner can detect this object and it can also calculate the distance traveled, the distance between the robot and the object. And how it works, it emits laser light and it calculates the time of return of this light, and then calculate the distance s. And let's say we also have some kind of sensor that can calculate the angle between this object and the front axis of the robot, or the heading, you can say. Then this robot is also equipped with a sensor, let's say a compass, that can tell the angle from the north. So this is, let's say this is a north, and we have the robot has some kind of compass, and it can tell what's the angle between the robot axis and the north. We call this angle theta. Okay, so now we have the theta, we have phi. We can calculate the internal angle, which is theta minus phi. Okay, so the location of this object is already known, and it is x naught and y naught. And the location of the robot with respect to this object is delta x and delta y. Okay, so now we have this all the required inputs, and what we want to calculate delta x and delta y, which is the position of the robot with respect to this this object. So once we have delta x, delta y, we can calculate the position of the robot in some kind of global frame, or the reference frame we have here. Okay, this is a reference frame. So how we can calculate delta x and delta y? It's just we can see that this is a triangle, and whose internal angle is theta minus phi, and it's just have, using the trigonometry, we can say that the delta y over s is equal to cos theta minus phi. Also, and from here we can calculate delta y. Because s is known, we also know the theta, and we also know the phi angle. So from here we can calculate delta y, and in similar fashion we can calculate delta x also. Theta minus phi in this case also s is known, and we also know the both angles, so we can easily calculate the delta x. So yeah, so that's how we can calculate the delta x and delta y, and then it gives a relative position of this robot with respect to this object. And since the location of this object is known with respect to this frame, this reference frame, so we can also calculate the position of this robot in some kind of reference frame. And the orientation is already known. Okay, so this was a very simple method of localization in which we are given with the distance and an angle. Okay, let's take another scenario, and in this scenario it is assumed that the robot is not equipped with the sensors that can measure the distance of an object from the robot. Okay, so there are no such kind of sensors available. For example, this robot is not equipped with laser scanner, let's say. So then how we can now localize the robot in the environment or in the map? So in this case we use triangulation method. So what triangulation method is, this is our robot and this is the object. So this is the object and this is our robot. The robot is in this case not equipped with laser scanner that can measure this distance from the robot to the object. So in this case we use triangulation principle to calculate the location of this robot with respect to this object. So how it works? We have some kind of other sensors that can sense the angle, this angle. Let's say this is alpha. It can be a camera that can see that how at what angle this object is located from the central axis of the robot. And then what else is there is the robot now needs a second measurement. For that, robot will turn and it will go from position 1 to position 2 at this position. So this is the same robot, it's not a second robot. It's the same robot that first took measurement of alpha at position 1. After that, it went from position 1 to position 2 and it takes a measurement beta. Okay, this time, yes, let's say from camera or any other kind of sensor that can sense this angle but not the distance. So yeah, and also what is known is that using odometry the robot also can measure this distance from position 1 to position 2, and using odometry or wheel odometry, using wheel encoders. So let's say this measurement was C, the distance was the distance between position 1 and position 2. Okay, now we have 2 angles and 1 length. We can also measure this angle, which is a sum of alpha and plus beta, and we name this angle as gamma. Okay, now we have 3 angles and 1 length. What we want to find? We first we need to find this length A and then this length B, because once we have the distance between robot and an object, then we can use same method as we used in the previous slide to localize the robot. Okay, so let's calculate first. Let's calculate B. How we can calculate B? So let's apply on this triangle. Let's apply sine, law of sine. So law of sines. So this law says that A over, okay, I forgot to mention this internal angle, sorry. This internal angle is alpha prime, and this internal angle is beta prime, which is, of course, it will be 90 minus alpha. Alpha prime will be. So now apply the sine, law of sine, and it says that A, this length of this triangle, divided by sine of the opposite angle alpha prime, is equal to B divided by its opposite angle sine of beta prime is equal to C divided by opposite internal angle sine gamma. So we have this relation. So we one by one we equate, and then we see what are knowns, and then we find the unknowns. So from this equation, alpha prime is known because alpha is known, and alpha prime is just 90 minus alpha, and then we can calculate the sine of this. We first equate these two, this left hand side with the right hand side, and here we know the gamma also, we know the C also, and then from here we calculate this A. So this A can be calculated by the comparison of this side with the right hand side, and after that we calculate the B. B can be calculated using the comparison of this side with this side. So here we know that beta prime, which is 90 minus beta, we know the gamma, we know the C, and from here we calculate the B. So once we have, okay, now we shall learn about what is robot's pose. In a 3D world, we have three axes: x-axis, then we have y-axis, and then z-axis. We have also a rotation along x-axis, then rotation along z-axis, and then a rotation along y-axis. So total we have 6 degrees of freedom. For simplification, what we do, we don't use all 3 coordinates, but we use only 2D. Like here we use only 2 dimensions, And in these 2 dimensions, we also use a planar robot. A planar robot is the one who don't have any third dimension. It has only 2 dimensions, and it can move along x-axis or y-axis, but only on a paper or a plane. So here we have this is our robot, and this is the some kind of sensor range in which it can detect obstacles. Okay, this is our sensor here, and it can detect some kind of obstacle in the environment. And this robot can move along x-axis, it can move along y-axis, and it can only rotate along z-axis. So it has 3 degrees of freedom. So what is a pose of the robot? In the 2D reference system, the position in this 2D frame, or the reference frame, and the orientation with respect to the x-axis, the angle theta. This is the position and the orientation. They combinedly they call pose. The pose of the robot is equal to position of the robot and its orientation. So we can call it x, y, which is the y coordinate, and the theta. This is the robot pose. Now we discuss about the mapping. So what is a mapping? Mapping is the procedure to model the environment. For mapping tells the robot that where the obstacles are located in the environment, or where the objects are located in the environment. What is the position of these obstacles or the objects in the environment. So this process is called mapping. Let's say in this figure, this is a 2D top view of a room, and in this room we have an obstacle. This triangular shape blue is an obstacle, and then we have free space here, this white space, and this room has the length and width of 4 meters. Okay, so in this direction we have 4 meters, also in y-axis we have 4 meters. And here is our robot. It can move freely in this free space, but it cannot go in this obstacle space, which is occupied space, we can say. So this is free space, and this one is occupied space, the blue area. So how the robot can make map of this room? Let's see. So by making map, it means that we mean that it has to tell that where the obstacles or objects are located in this room. Okay, so this is the one purpose of making the map. We already talked about the occupied space and the free space. The occupied space is the space where the obstacles are located, and the free space is the space which is obstacle free, and the robot can also freely move there. Now we start with making the map, how we can make the map of this above room. Okay, although there are other types of maps also, there are continuous maps, there are probabilistic maps. We only, in this lecture, we talk about discrete maps. Okay, in discrete maps, what we do, we divide our environment into small cells or grids, you can say. So this was the original, this is a grid, same equal to the size of the room above here we have discussed. So from here, this room, what we did, we put a grid on this here. And initially, our robot, it doesn't know that where the obstacles are located. Okay. What it does is it only divided this whole room into boxes or cells of 1 meter length and 1 meter width. It must not be always 1 meter. It can be of any size. Any number of cells can be there. And the smaller the cells, the better is the resolution of the map. So more small obstacles can be detected with the small cells. So what the robot will do, robot will start moving in this room, and where it finds an obstacle, let's say it turns here and it sees there, it will not go there because there is already an obstacle. So if I see, then wait, let me see. Yeah, so there, because the triangle goes like this. Right? I will change the color so it's visible easily. So here the robot will go, the obstacle is like this. Okay, so for robot, when the robot will reach here at this position and in this cell here, okay, so the sensor will detect an obstacle here, and then because we have a discrete map, and the whole cell will be considered as an obstacle. So this whole cell will be an obstacle. Because it's a discrete, the cell can be either empty, completely free, or it can be completely occupied. Because this cell was half occupied, so we take it as a full occupied cell, and this is blocked. And similarly, this will happen in the other cells also, and the robot keep moving. So these all cells will be considered as obstacles. This one here also, this one also. But for that, robot has to move a little bit more in every direction, every orientation. It has to move, and then it can detect all the obstacles in the room. You can see the lower obstacles, they are not visible from top, from the current location of the robot. So what the robot will do from there, to detect the lower obstacles, the robot will move from here back. Here, it will go back here, and here it can detect the obstacles, the lower obstacles from here, from these cells. And you see that robot is trying to find the location of the obstacles, but also the robot knows its own location also. For example, when the robot was here, it knows that it is in the second cell, in the from x-axis it was 2 and the y-axis it was 1. It knows the coordinates of its own, and then it can tell, okay, and at this point, at this cell, the obstacle was present or absent. So after making the complete map will look like something like this. If you see that, this is our discrete map of our original room. The original room looked like this here. So this was the original room here. And notice that after after making a discrete map, the discrete map look like this here. So this is the occupied space, blue color, and the other cells are empty, and they're called free space. These kinds of maps, they're also called binary occupancy grid, because it's a grid-like structure. And these discrete maps, they're useful because they can be used in digital computers and microcontrollers, okay, because they resemble like matrices. A matrix has some columns, and then it has some rows here, and then we can manipulate, we can perform matrix operations on these discrete digital maps. So the free space is represented by 0, and the occupied space is represented by 1. So 1 means there is an obstacle and this cell is occupied. The green means this is free space. So later for path planning, we use these kind of maps to plan a path to avoid obstacles and to reach some kind of goal. Okay, so now we shall see the robot's architecture and some types of architecture the robots have. So robot architecture shows how the control software of the robot is organized. Okay, so it tells how the robot decision making process and reaction process, or how they work, and how the internal software architecture of the robot is organized. So we have different types of paradigms. The first is deliberative paradigm. In deliberative paradigm, the robot architecture consists of sensing, then planning, and then action. So it means that the robot get information from the sensors, and then it do some kind of planning from this information, and then it performs actions. So usually the robot has to do mapping. It needs a world map, or it makes a world map, because for planning you need some kind of model of the environment, so you can plan in this model. So because planning can be computationally expensive, so this can be considered, this thing can be considered as one of the disadvantage of deliberative types of control architecture, you can say. So because the robot, for every information, robot needs a map, or you can say you need to update the map or make a new map, and then it has to perform planning, and this requires a lot of energy and time. So that's why this is one of the disadvantage of these kind of architectures. But the advantage might be that it gives better results, because it analyzes things on higher level. So it might give better results. The second type of robot architecture for control is the reactive paradigm. In this case, the robot has only sensing and acting ability. So robot sense environment, and then it performs action. So there is no planning involved. So this is kind of simple, you can say, simple kind of architecture for robot to have. Another advantage of this is that it doesn't require world model. It means you don't need to make a map of the environment to navigate in the environment. And of course, it also doesn't need, it is also then, if it doesn't need planning and also doesn't need a model of the environment or a map of the environment, then it means it's less computationally expensive. It means it's fast, it's very reactive. So this is one of the advantage of this kind of architecture, that it is more reactive, it's fast to the changes, and it is less computationally expensive. The disadvantage could be that it only sees the local environment. It doesn't know the global, because it doesn't have a map of the environment. It cannot see the global perspective of navigation or planning, and which is why it can be not so accurate. It cannot give you the best solution always. Then we have hybrid type of architectures, and in hybrid we have seen that in the previous two deliberative and reactive architectures we have some advantages and disadvantages. So to get best of both of the architectures, we combine both of them and we call it as a hybrid architecture. Okay. Now we shall learn about algorithms and their types. So what is an algorithm? Algorithm is a set of instructions used to solve a problem. So algorithm can be any computer program, you can say, that can be used to perform a task, a specific task, or to solve a problem. This is a simplest example of an algorithm. Okay, it might be a pseudocode also. I mean, it's not actually a actual programming language, but only some kind of instructions to show how the algorithm works, how actually the programming code works. So the instruction can be moved towards the goal, follow the obstacle, and repeat the task. So this is a simple example of an algorithm. Then we have types of algorithms. We have deterministic algorithm. Deterministic algorithm is the type of algorithm which has same output for same input. It means that if the input is same, then the output will always be same for these kind of algorithms. For example, if the robot is given a same environment, and if it's using a deterministic types of algorithm, then for same type of environment, it will do same kind of navigation every time. Then we have opposite of deterministic, which is a random algorithms. And random algorithms can have different output for same input. Okay, because they work on some randomly generated numbers, so their output varies every time and it's not same. Then we have offline algorithms versus online algorithms. Offline algorithms require some kind of input before they run. For example, there are algorithms for offline path planning, and they need a map of the environment before, and then on this map, the algorithm, we run the algorithm, and then they calculate the path in this map. Okay. In the opposite of this offline, we have online algorithms, and online algorithms are, they need they get their input while they are running. For example, a robot is moving through the environment, and also it's getting map of the environment. Meanwhile, the algorithm is running and the robot is moving, and yeah, so both things are happening in the same time. So this is online algorithms. So the map is also the map data is also being you can say the readings from the sensor, okay, they are being obtained by the algorithm, and meanwhile the algorithm is running and the robot is also moving. But in the other case, the offline algorithm, first the algorithm needs a input like a map. It runs after that once the path is there, and then robot starts moving. So it was some kind of, you can say, step-by-step approach. Then we have exact versus heuristic algorithms. Exact algorithms try to give you can say the best possible solution, which is close to the actual best solution we have. Okay, for example, when you run this kind of algorithm, they always do so much calculations to get a best possible solution, and the solution is guaranteed that it is the best solution, okay, and close to the actual best solution. And every time you run, they give you the same best solution, and there is also you can say guarantee that they will give you the best solution. Then we have heuristic type of algorithms. They try to give you the best solution, but there is no guarantee, okay, because they don't follow all the standard procedures, and so they sometimes they don't give best solution, so there is no guarantee that they will always do. The advantage of these heuristic algorithms is that they are faster as compared to exact algorithms. So exact algorithms, they give best solution, but they are slow. Heuristic algorithms, they are faster, but they don't guarantee the best solution. After that, we have brute force algorithms. Brute force algorithms are, I say them, are naive kind of algorithms. What they do, they try every possible solution, and then they try to pick the best solution, okay? So that's why they are very computationally expensive. They need a lot of time to calculate the solution, to find the solution, and yeah, so they're not, you can't say that they are very smart algorithms, because they make so many mistakes. They try every possibility, every solution, and then pick the best solution. After that, we have the greedy algorithms. Greedy algorithms, as the name suggests, they always pick the locally best solution and hope that they get the globally best solution. But it's not always the case. Because of their greediness, they may not be able to find the best solution, okay? Because they only see the pick the best locally, okay? not the global best. Finally, we have dynamic programming type algorithm. These types of algorithm, they used for optimization, and how they work is they divide a problem into sub problems and then try to solve the sub problems to find the best solution. Okay, we have seen already different types of algorithms, and now we shall see what are some performance parameters of algorithms. We have an algorithm. How can we say that this algorithm is better than other algorithms, or how can we, there are many algorithms we have studied. So how can we compare what are the parameters, performance parameters on that can be used to compare these algorithms? So the first one is the completeness. We call an algorithm a complete algorithm if it finds a solution if the solution exists, and if the solution doesn't exist, the algorithm ends or fails to find the solution. But there are also algorithms that are not complete because the solution exists, but these types of algorithms, they fail to find the solution. Okay. Then we have optimal algorithms. Optimal algorithms they try to find always the best solution. Okay. When you give them a problem with multiple solutions, so they will always give you the best solution. Optimal means to maximize or minimize some parameters. For example, if you want to find an optimal path with respect to energy consumption, then there are algorithms that can give you this that can minimize energy consumption and give you the best solution. Then there is another performance parameter is a time complexity. It is the time taken by algorithm to compute the solution, and they are and usually it's in relation with the input size, input data. So as the input size increases, what is the time complexity, how it affects the time complexity. So some of the algorithms we studied in the previous slide, they have a better time complexity. It means they can compute the solution very fast. But some others, they require so much time to calculate the solution. So they are not that good enough. Okay, then we have space complexity. Space complexity is the amount of computer memory required by an algorithm to find a solution. Okay, this is again related to input size also. So when the input size increases, it affects the memory of your computer. And again, some algorithms, they require low space, low computer memory, while others, they require a lot of memory. So yeah, so these are the 4 performance parameters we use to compare the algorithms and their performance. Some algorithms, they are complete, others are not complete. some algorithms are optimal, they give the best solution, while others they give like not so, like less than optimal solution, you can say. Yeah. Okay, now we shall see some algorithms for navigation of a mobile robot, and these kind of algorithms we call them bug algorithms. Bug algorithms, they are inspired from insects, you can say. Simple insects, how they navigate through the environment. So these bug algorithms are inspired from insects like flies or some other kind of insects. Okay, so they do not require global knowledge of environment. Instead, they require only local knowledge. So it means that they don't need a complete map of the environment. They don't need a model of the environment. What they need is only that they need that what's the obstacle in front of them or in the side of near. They need the information about the obstacle that is close to them, not about far away or other obstacles that are not in range. Then we have these kinds of robots. They are equipped with tactile sensors for obstacle avoidance and optical encoders for localization. So these kinds of robots, they have this is a robot hour. So these kinds of robots are equipped with optical encoders on the wheels for odometry or localization, you can say, and they have also some kind of sensor for like ultrasonic sensor or tactile sensor for obstacle avoidance. So they have very simple commands. For example, move toward the goal and follow the obstacle boundary. So their architecture, their software can be very simple. So you can call them like very simple kind of robots that can autonomously navigate. Okay, so in the bug algorithm, the position of destination or goal is known. Yeah, that's important. The robot has to know where the goal is located. Okay, its coordinates. Also, the robot has to know where the robot is located and where the if there is an obstacle, it can detect the obstacle. So yeah, let's start with our simplest algorithm. It's a bug zero algorithm. In the bug zero algorithm, this is our the figure you are seeing below. This is the blue color robot, then we have an obstacle, and then again black color obstacle, and this red color is the target or the destination. Okay, and this is the start position we have. So now we see that how the robot will navigate in this environment using bug zero algorithm. So I will change the color of the pointer so we can draw a complete path of this robot. So from the start position, the robot start moving toward the goal. Okay, as soon as it detects an obstacle, it start to take a left turn and start to follow the obstacle. The turn it has it can be programmed as right turn or left turn. It depends upon the programmer. Then the robot keep following the obstacle, and as soon as the obstacle is finished and the robot is available to move again toward the goal or the target, it will again start moving toward the target. As soon as it detects obstacle again, then it will start again left turning and follow the obstacle. Okay, and as soon as the obstacle finished and the target is the robot can follow the target, it again start moving toward the target, and when it reaches the target it stops. So this is a very simple algorithm for robot navigation. It doesn't require a map of the environment, not the planning also. So, but it has some issues that this kind of algorithm, it may get stuck in certain types of situations, you can say. Okay, and these situations can be some certain types of puzzles. For example, this type of puzzle we have here, and here is your robot is here and your target is here. So if you use Bug0 algorithm to navigate in this kind of, so these are the obstacles. We have obstacle. I should make it with black color. So in this scenario, the bug algorithm will get stuck because the robot will start moving toward the goal, then it turn left, and as soon as the obstacle finish, it again move toward the goal, and then it turn left and follow the obstacle, keep following the obstacle until it reaches the same position, and it will keep repeating same thing again and again. So yeah, so that's why we needed some improvement in Bug0 algorithm. So some guy came up with Bug1 algorithm. So Bug1 algorithm, how it works is that Bug1 algorithm, this is the start position of the robot, and this is a target, and then we have same kind of obstacles. The robot start moving towards the target. As soon as it detects obstacle, it takes a left turn and start following the obstacle. Keep following the obstacle till it reaches the hit point. So yeah, so this was a point where it started to take the turn, and from when it reaches here, in this all this circular path around the obstacle, all points here, it calculates the distance of these points to the target. Okay, and select the point which is closest to the you can say closest to the target. Okay, so let's say this is the closest point. So the robot, let's say this is the closest point here. So the robot will again move toward here, and from this point the robot will start moving toward the goal. Then it hit again the obstacle, and then it start moving following the obstacle again. And then it came back to this point, and here it again calculates which point is closer to the target. Okay, so it calculates the distance from all the points on this loop, and it selects the point which is closest to the target, which is, let's say, this one. And then the robot from here, it takes again, travels to this point again, and then again the robot start moving toward the target and reach the target point or the destination. So as you can see, this Bug1 algorithm, it has some disadvantages because it takes a lot of unnecessary kind of turns, and it's time consuming, it's inefficient, So also it's very, looks like very naive kind of algorithm. So so definitely there is a room for improvement. So in the later, you see that what was improvement done. So some guy came up with this BUG2 algorithm. BUG2 algorithm, how it works is that in this case, this is a robot, and the robot at the beginning, it makes some kind of you can say a line from imaginary line, you can say an imaginary line from start position of the robot to the target. So this is our imaginary line, and then after that the robot starts moving directly toward the target. As soon as it detects obstacle, it takes left turn and start following the obstacle. It keeps following the obstacle till it reaches this line. Okay. As soon as it reaches this line, it keeps following the line again. There is another obstacle. It will take a left turn and follow the obstacle. Keep following the obstacle till it again hits the line, and then it start following the line and reach the target. You see that this algorithm is much more efficient as compared to BUG1 algorithm, because it doesn't have these unnecessary rotation around the obstacle, which wastes time and energy both, and the path is also shortest. So yeah, so they are efficient than BUG1 algorithms. Okay, so this was the end of our lecture today. Today's lecture, we have learned about navigation. We defined navigation. We also learned about how autonomous robots can navigate. And then we discussed about the localization. We learned about what are the errors. We learned that there are some errors, uncertainties in the odometry. So we need localization to improve the errors in the odometry. And we have seen that how we can localize object or localize a robot with respect to some kind of objects in the environment. We also learned about triangulation method to find the position of the robot. And then we talked about mapping. Today we learned about what is mapping, what is how we can make a discrete map of the environment, and what is the advantage of using a discrete map. Then we briefly discussed the robots architectures, 3 different types of architectures and their advantages and disadvantages. We talked about algorithms. What are the algorithms, their types, and how these algorithms can be, their performance can be compared with each other, and what are those parameters for performance comparison. And finally, we talked about the bug algorithms, and we have seen 3 different bug algorithms for robot navigation: bug 0, bug 1, bug 2. We also seen that what are the some advantages and disadvantages of these kinds of algorithms. So yeah, so I shall end this lecture now, and thank you very much.